Okay, we're going to come back and we're going to wrap this thing up talking about exponential decay. Exponential growth we looked at previously, n equals n sub 0 e to the kt. Exponential decay, exact same formula. Exact same formula, okay? Decay means that you're losing quantities. Okay, we'll look at radioactive decay. Okay, we'll look at half-lives. Okay, it's all that simple. Okay, so let's take a look at an example of a radioactive decay problem. Okay, all right, here it is. A radioactive substance decays according to the equation m equals 15 e to the negative 0.0018 t, where the mass present is measured in grams. That's the mass, okay? And the time is measured in years. The percentage of the initial mass present to the nearest whole number after 25 years is what? Well, again, it's that simple, okay? All we have to do is we have to put 25 into this equation. What is that equation? It is the future quantity is equal to the present quantity, n0 e to the kt, okay? Actually, it's more like n is the present quantity, n sub 0 is some initial quantity, okay? Because the present quantity should be less than the quantity stated from the beginning, okay? So, okay, in this instance, all we have to do is put in the value of t as 25 years, okay? And it's asking the percentage of the initial mass. Now, what this is saying, that the original mass was 15 grams, okay? So whatever we get, we're going to take it as a ratio over 15. So here we go, okay? Our equation here is, okay, 15 e to the power negative. Decay is going to have a negative growth constant, negative 0.0018 times 25. Okay, that should do it. So our quantity is 14.33 grams. And what percentage of that, of the original 15 grams is that? Well, that's a 95.6%, okay? So it's 95.6% remains. 95.6% remains. Let's work with this equation. If we're talking about a half-life, that means we want to know how long will it take for some substance to decay exponentially to half its initial quantity. So in this case, we're talking about half its initial quantity. We're talking about n equaling 1/2 of n sub 0. That's a half-life. So let's work with that, okay? Let's put that all down and work with that and see where we go, okay? So we're talking about 1/2 of n sub 0 equaling n sub 0 e to the kt, all right? Obviously, n sub 0 is independent, so we're down to 1/2 equals e to the kt. Take the natural log of both sides, and you got natural log of 1/2 is equal to ln of e to the kt, which is simply kt. So here we have it. Kt is equal to the ln of 1/2, which means if you have the constant and want the time, time is equal to the natural log of 1/2 over the constant. Or Or if you have the time, the constant, and you, well, if you have the time and you want the constant, going back, the constant is going to equal the natural log of 1/2 over the time. So let's see. Here we go. Radioactive substance, iodine 131, is used to diagnose thyroid gland cancer or whatever. The half-life is 8 days. Its mass decays according to the equation, okay? Where M is measured in grams. The decay constant is, okay? And what is it that we're after? Okay, its mass decays according to the equation. This is a good one. I don't think it's a question. All right, so, oh, it has a half-life of 8 days. Its mass decays according to the equation. Mass equals A e to the negative kt, where m is measured in grams and t in times. What is the decay constant? The decay constant. Well, here it is. The constant k is the natural log of 1/2 over the time. So it's simply k is going to equal ln of 1/2 over 8. Simple enough. It should have a negative because obviously the natural log of anything between 0 and 1 is going to be negative. So here we go. All right. Turn the calculator on. Clear it out. Natural log of 0.5, that's 1/2. Okay. Divided by 8. The growth decay constant is negative 0.0866. K is equal to negative 0.0866. So its decay constant is negative 0.0866. That is exponential decay. Again, it is exponential growth in reverse. Same formulation, the constant will be negative. The constant will be negative because the future quantity or present quantity is going to be less than that which you started out with. Okay? So if you're interested in half-life, then the quantity, okay, that you end up with is half the original. So the equation simplifies down to 1/2 is equal to e to the kt. Natural log of both sides allows you to solve for k in terms of t, okay, or t in terms of k. The t being the half-life time, k being the half-life constant, okay? T is natural log of 1/2 over k. K is natural log of 1/2 over t, okay? There you have it, exponential decay. Exponential decay.